Okay, chapter 4. Okay, chapter 4, we start to look into impulse and momentum. So chapter 3, we're done with principle of work and energy, conservation of energy. Now in chapter 4, we start to look at impulse and momentum. Okay. So when you talk about F equal to ma, previously our A we can define as V divided by T. And when we integrate, we pull the dt to the force side. We pull the dt to the left-hand side. We can integrate the force and the velocity, right? So force multiplied by the time change. And on the right-hand side, you will get integration. You get V2 minus V1, right? You will get this equation. F T is the impulse. Right-hand side, mv is the momentum. Okay, Ft is the impulse, and right-hand side is the impulse. So if you see the question asks you to use principle of impulse and momentum, it means it asks you about momentum. Or you write in integration. Okay, and there's a summation there, meaning there is summation of all the force with the time, all the force with the time. So if you have a lot of force you have seen before, gravitational force W also part of this one, friction force also this one, and many more, as long as a force vector. Remember, this is an important equation. It will cost you 2 marks if you write this one out. So write force, time, momentum on the answer sheet. So this is called principle of linear impulse and momentum. So if you look at this principle of linear impulse, what parameter you're focusing on? Force, time, mass, and velocity. So this equation, again, what can it help you to solve? Normally, it will ask you to solve time and velocity that is unknown, usually V2, right? Chapter 3, equation of work and energy, principle of work and energy will help you to solve velocity. Same with this one. This one, when you have time and force. So we will use capital L to represent momentum in this chapter. Capital L to represent mv, right? The unit will be kilogram over meter second. This is a linear momentum, So on the left is linear momentum, on the right is linear impulse. We will use capital I to represent integration of force and time. So on the top here, if your force is changing, if you plot force versus time, the area under the graph will be the top one because the force is changing. But if the force is constant, you get a square. Okay, you get a square. So you can write the top form or the bottom form, same. Bottom form will give you a better solution where you group all the event happen before on the left hand side, and all the component happen after on the right hand side. Top and bottom still give you principle of linear impulse and momentum. Okay, so again, what is momentum? Momentum is mv, impulse is ft. Ft give you impulse, mv give you momentum. So you can draw diagram before and after. So for example, the left hand side, mv, is the particle with the mass and velocity 1 pointing this way. You just assume that it's going that way. It's called initial momentum. There's a change of impulse, ft, so you group all the force acting on the object, multiply by the time, it's called impulse diagram. Combine these two will give you final momentum diagram. Okay, so sometime this is another diagram that you might need to learn beside the free body diagram. In chapter 4, this will help you to solve normally the middle part, the impulse component. So if you break this diagram on the top of the screen here into x direction, y direction, z direction, you can rewrite the momentum, linear impulse and momentum equation in the x direction. For example, mvx plus fxt plus mvx2. You can break into this way, and then only focus on x direction. You solve that one, you might able to find one of the missing parameter. Same with y, same with z. Okay, you just repeat the initial formula, break them into x, y, z. Same. Then if you have a group of atom, you just group them together lah. You just use the sum to form all the. This you'll see this one when you talk about rigid body later. You are now still at particle, so this one later we'll still revisit this idea. Okay. Right. Okay. So it's still the same formula. Momentum mv, individual one, you sum all every one of it, plus impulse ft, you sum all the individual force acting on that. Same with the mv2, same, right? Same, huh? Then in later chapter, when we talk about rigid body, you need to find the center of gravity. In this case, we just give you early introduction first. Later, when we talk about rigid body, we'll emphasize on this equation. So how do you find location of central mass? You take Vg equal to sum of individual mass and velocity. Okay. Then you put inside there the equation. Right? You'll see this one when you talk about rigid body. Let's apply what we learned for one. So you see this one in your chapter 1, example 1 question. Now we try to apply the same information but using chapter 4 equation, which is principle of linear impulse and momentum. So you are having an object pulling by 20 Newton at 45 degree. This is have a contact of surface, so there must be friction and normal force here, right? So 100 kilogram original at rest, we have V1. Smooth horizontal surface means your friction is 0. If a towing force 200 Newton is given, 45 degree for 10 seconds. So time is given. So you have force, you have time. Force, time give you impulse. Right. So from the question itself, actually you can predict what is the chapter that you have. Right. So force have, time you have. Determine the final velocity and normal force with the surface which the surface exerted on the crane during the time interval. This is a normal force that you want to find. So nothing complex here. Draw free body diagram. Put in all the force that you see. Usual with the weight, friction force, and external force. Normal force. Friction force here is 0. Right. So in your free body diagram, start from chapter 3 onwards. Now we're in chapter 4. You start to using normal force already. All right, then you overlap with the kinetic diagram with the V. V move to the left, move to the right as we assume because of the force direction. Okay. Then you pull in the principle of linear impulse and momentum. Momentum before the incident plus the change of linear impulse equal to the momentum after. You look at x direction only, and then you solve for x direction, you solve for y. Same equation, but they break into two directions, x direction and y direction. So I plug in the direction, the information. mv 0 because velocity in x is 0 before the start, it tell you from the rest, so 0. What is the impulse that you have? Force times time, but force, it must be in the x direction because you are looking at x direction. So this one changed to x direction, cos 45. 10 seconds, m still same, velocity you want to find. So from here you find your v2. Vx2 means the vector in x direction. You do the same for y. One missing is your normal force, right? My in Vy 0 because there is no velocity from the starting. But however, for the y, there is an effect of normal force already. Normal force multiplied by time. Although normal force, it look like it doesn't do anything. But when there's a force and the time, then there's an impulse there. Okay, so don't confuse this one with chapter 3. This one, normal force, when it comes to impulse, when the force and time, then there's an impulse. Then gravitational force, W, and the time, and the force, and the time, equals 0. Vy 0 because velocity do not appear in y direction. Your velocity is in the straight line. Example 1 here is in the flat surface. So you need to ask yourself, if I slanted my floor at a certain degree, what happened to my V? How do you solve the question? If we change the surface angle, right? This is a flat surface, so everything is simplified. So here you find your normal force. You can use the same one, same question by going back to chapter 1 or chapter 2, F equal to ma. You can still do the same. You can still get the same answer. Chapter 2, F equal to ma plus the motion equation, you'll still get the same answer. Okay, one more example, I think then we call it a day. Okay, one more example. Just now it's a flat surface. Now we push the surface up, and now object is slanting down with the force pulling down. So V is given, so mass is given, variable magnitude, your P variable here. Just now, example 1, your P, your force is constant, but now your variable with time, 100t. Determine crane velocity 2 seconds after P is applied. Initial velocity given, and the coefficient friction was given. So you know, in this case, we want you to consider the friction force. So by having this one, I think most of you already expert how to convert this diagram into free body diagram already. So draw free body diagram. You always have weight, always have contact surface. So contact surface always have normal. Okay, normal always 90 degree to the surface. So friction force, because force is pulling down, friction force opposite, and put in the force there. In this case, most of the time I will focus all my force along the surface rather than I chasing after the force. I put all my force along the surface. So I put in the principle of impulse and momentum. Momentum before plus the change of impulse plus the momentum. So what happened to your Vx? Mean x, in this case, my x is positive, go down. Okay, in this case, my x is go down to help me to to remove all the negative sign. My x here, I follow the surface, the motion direction, x. So my mv, I don't know. I just put it back in x direction. My impulse, I have p force, and the time, my p is in the equation, so I have to put in integration force and time. Then I have friction force, I have normal force in y direction, so I don't include in the x direction equation. So I don't include this one. So weight, I change to x direction and y direction. So x direction is positive. So here I see W sine 30t and the MV x2. I put in all the value, I substitute. Here you need to recall your integration scale. 100t dt, you get what? T squared divided by 2. So you get 50t squared divided 50t squared here. Okay. Okay. Then you solve. Here you before in the x direction you have one unknown and two unknown. Okay. So you do the same for y direction, but now my y direction is go up positive, but 90 degree to the surface. So my y, I just solve it using statics equilibrium. I just solve it using equilibrium. All the force in y equals 0. I can find my NC. Okay. Once I have my NC, I substitute back to the previous one. You can also repeat the same with this equation, but in y direction also can, no problem. But because of equilibrium, I just use statics solution. Then you can find the V2. But this one is in, sorry, wrong notation. It should be Y2, not X2. Sorry, this one, correct. This X2, correct. Substitute back to the X direction. Yeah. Another set of solution is that I solve using chapter 2, F equal to ma. Just now I solve using linear impulse and momentum. Now I solve using chapter 2, F equal to ma, same. Same, you substitute all the force on the left-hand side and ma on the right-hand side, but in one particular direction, x. Then recall definition of acceleration. A equal to dv dt, you pull it out, you integrate the A, because your A is in the in the equation. You integrate 0 to 2 seconds, you get velocity 13.7. Okay, this is chapter 1 equation. F equal to ma plus chapter 1 acceleration, this one. Okay. All right, so I think we stop here. We continue example 3 next week. Huh?